we study real classical laminate theory. Last week, I just like to remind you what we covered last week. Last week, we covered there. We talked about the fiber and matrix properties and how to get the stiffness, and strength for different fiber volume fractions. And we also the compliance matrix and stiffness matrix, which we will derivation of laminate theory. Now today, I will check whether my mic has some problem. Let me see. Stiffness is that we have an axis which is aligned with fiber. So x-axis is aligned with fiber directions, and y is perpendicular to fiber direction. So we have x, y. This will be called on axis. These x and y, x, y coordinate will be called on axis. On axis. Again, x is the along the fiber directions, and y is the perpendicular to a fiber, and this is the on axis. Very important to understand the name of this axis. Sometimes we call x1 and x2, depending on the notation. So either x and y or x1 and x2, but mainly x and y. Mainly x and y. But the reason I'm mentioning about this x1, x2 is that depending on the text, depending on the authors, they may use x1 and x2. So when you go through some theory, you need to make sure which axis indicate to which axis, which notation to which axis. Okay? In our textbook, in our lecture, xy is usually mean the on axis. So I like to just summarize what we covered. This is the x-axis, this is the y-axis, and sigma, which is the sigma x and sigma y and sigma shear. Now this is the given as q xx, q xy, and q xs, and q yy, and q ys, and q ss, and multiply by epsilon x, epsilon y, and epsilon s. So in short, we Q is given Q matrix and epsilon matrix. Again, Q and epsilon, and they are all in own axis coordinate system. How do we get this Q matrix? Q matrix, define the material property, we usually use a form called compliance matrix. Like that. Of course, this compliance matrix is the inverse of the Q matrix, and S matrix, or you can say Q is the given as the inverse of a compliance matrix, and compliance matrix is the defined as the material property in engineering material property 1 over EX, UX, and EX. And 0, and 1 over EY, and 0, and 1 over ES. Like that, this is the symmetry. So this is the compliance matrix. Now EX, stiffness in along the fiber directions. So this can be measured from experiment, of course. So EX and EY and Poisson's ratio and ES either can be experiment or either can be from micromechanics. Can be calculated micro mechanics. And in this case, we need to have a material property from a fiber and matrix or resin. Okay, so either experiment or micromechanics. Or which way do you prefer? Of course, we like to minimize the experiment. So micromechanics is always preferred. And once we have a fiber and matrix property, we can cover many different material properties for different fiber volume fractions and easily predict for this stiff material property for different temperature and so on. So it's extremely important to understand micromechanics. But in reality, the micromechanical prediction can be different from an experiment, and we need to, depending on the situation, we need to understand both. So anyhow, from now on, we like to start from this material property and Q and so on. This is the own axis. Okay, this is the own axis definitions. Now, what we like to do today is that ob axis. What is the ob axis? Well, ob axis is like some angle. Now, fiber has the some angles with respect to reference directions. Okay, reference direction, and this is what we'll call ob axis. So there are are many reasons, and it's very important to well understand the O-axis stiffness of a unidirectional composite. And the most important point in understanding composite is to understand anisotropy. Well, what is the big difference between anisotropy and isotropy? Well, that is the which is always related to our axis. Okay, so again, to fully follow the theory and fully understand the composites design and analysis, extremely important to well understand axis. Now, as I said, what is the O-axis of the unidirectional composite? So fiber, this is the as we already defined, this will be X and this will be a Y. This is on axis, and now this is the this on axis is rotate some angle with respect to reference direction. I will call reference direction as the x1 and x2. So xy is the on axis, and x1 and x2 for off axis. So what is the relations? We need to understand what it means by the relations. There could be several physical quantities such as stress and strain and stiffness, and there are many physical quantities, and there are relations between relation of the such physical quantity between on axis and off axis. So this is the chapter or section most important in understanding composites. And now coordinate transformation and strain transformation and stress transformation and over stiffness transformation. You need to follow, you need to understand coordinate transformation and strain transformation, stress and over axis. We will go step by step. The coordinate transformation is similar to vector transformations, and in terms of order, vector is the first order tensor, and strain and stress is the second order tensor, and over stiffness is the order of fourth order tensor. Well, tensor sounds strange to you, but understanding coordinates is important to understand the order of the tensor. Okay, so let's define the coordinate system. The mechanical property of isotropy material. Now, isotropy material do not change over the direction. What it means is that, say this yellow material is isotropy, then we have some fixed coordinate. X, Y is fixed to these materials, and it rotates. This is the X prime, and this is the Y prime. Sorry, this is the X and Y. This is the fixed and rotate. The material properties do not change. In other words, let's say we apply some stress, and we apply some stress here. The material property remains the same. Why? Because this is the isotropy. So either xy and x prime, y prime, all the material property defined with respect to xy will be the same as the material property defined as the x prime and y prime. That's why it's called isotropic material. Now, all axis, on axis indicated by x and y, and all axis, as I mentioned, can be indicated by x prime, y prime, or sometimes x1 and x2, depending on the situations. And now this is the triangle data with respect to what this is the, you can call a reference direction, reference coordinates, or this can be called orb axis. So the stiffness and compliance metrics for orb axis, compliance and orb axis stiffness and orb axis stress, we use a bar. Okay, we use a bar to indicate different coordinate systems. So sometimes we use epsilon bar or epsilon prime or sigma prime, the sigma bar. They mean orb axis quantity. Okay, this is the orb axis coordinate system and symbol. Now, let's try to understand the vector transformation. While we used to study this in undergraduate, and this is the fundamental starting point of understanding coordinate transformation and even understanding the concept of the tensor. Say this is the xy, and there is x prime and y prime. Now there is a quantity, it's just a vector, some directions. This is the f vector. And to indicate this f vector, we can use a different coordinate system. Say we can use the either xy or we can use x prime and y prime. But the quantity should not change. Only changing is that the components depending on coordinate system. So if we use the x prime and y prime, then this is the x prime and this is the y prime. So this much will be x prime, fx prime. This will be fy prime. Now, if we use the xy, well, this much will be the fx, and this much will be fy. So as you can see, this f quantity does not change. That's the key point. Okay, does not change, but depending on the coordinate system, to indicate this f, we may have this much components, and if we use xy, we will use this much component and this much component, right? Again, I will redraw here this. Oops, this. So we have a f. This will be a fx prime, and this will be fy prime. And I will use a different and this will be fx, and that will be fy. Okay. So again, the quantity of f does not change, but these components are changing depending on the coordinate and the angles. You need to remember that the angle is between the two coordinate systems. So this is the angle. Now, this, for example, fx, this fx has the relations with fx prime and fy prime. We know these relations. This is the vector transformation. And this fy is also given as fx prime and y prime. This fy prime, this fy has relations with fx prime and y prime. We're not going to drive this relation, but we clearly know there is relations like that. And simply, we can say fx and fy, backup matrix form. We have a cosine theta and sine theta and minus sine theta and cosine theta. And this is the fx prime and this fy prime. Again, this is the relations between the component, the vector component. We can call vector transformations, and vector is the first of a tensor, and this is the relations. Relation between components in two different coordinate systems. That two coordinate system has the angle theta. And sometimes it's confusing. There is whether this cosine theta is clear, and there is a sine theta and sine theta. But sometimes it's confusing. There is a minus here and there, but understand here is the minus. And always this x and y coordinate system comes from left hand side. The x prime and y prime is on the right hand side, and there is a minus. In fact, the easy way to understand is that here is x and here is x prime. X and x prime. What is the angle? Well, theta and cosine theta. Always the cosine of the angle. And in other words, say this is the x and this is the y prime. So this is the x and this is the this is the x and this is the y prime. And since this is a theta, and the angle of this, again, cosine 90° minus theta will be the sine theta. That's why it is a sine theta. So whatever quantity here is the cosine of those two axes, these corresponding components. And for example, y and x prime, where is the y? Y is this one, and x prime y is this one, and x prime is this. So the angle will be 90 plus theta, and cosine of this is always minus sine theta. That's why we have a minus sine theta. And this one, y and y prime, of course, this is the theta, so will be the cosine theta. Okay, so cosine, sine, minus sine, and cosine theta is the component we need to understand. Again, this is the first of the tensor transformation. Now we are trying to transformation. To calculate transformations, we need to redefine the strain components. Say this is the 3 by 3 matrix. The strain is always the second of the tensor. In XYZ coordinate system, it has always the 3 by 3, and 3 by 3 we use this order. So epsilon xx, yy, and sigma z, and then yz, and xy, and xz, and xy. And this is the order we are using, and make it as a column, not the data, but it's a column form. So 1, 2, 3, 4, 5, and 6. And epsilon x and epsilon y and epsilon s, because the two-dimensional, we use only fourth and second and sixth components. And be careful about the definition of this. This is the tensor strain, and this is the engineering strain. So sometimes called gamma, which is twice of the tensor strain. Now, what we like to do is that we have a definitions of the compliance and stiffness. This is the ob axis, right? This is the ob axis, and this is the ob axis, and the stress. Okay, this is the stress, and this is the stress, and this is the strain. The stiffness or compliance matrix is defined for the ob axis and strains is that this is the stress sigma 1 and sigma 2 and this is the strain in epsilon 1 and epsilon 2 and epsilon x6 applied to ob axis coordinate system. Now, compliance is defined like that, and stiffness is defined as this, and between them we have a inverse relations. So if we have a stiffness and multiply by the compliance, we will have a strain. And reversely, if we have a strain, we multiply by the tuba, we will have a stiffness. This is nothing new, but we just redefine this definition of the stiffness and compliance of the ob axis. Now, as we did here, we have this transformation matrix. Now, how about the strain? Well, strain, of course, has the transformation rules, and we see all the derivations. We just have a final form, and we like to have, say, epsilon xx and epsilon yy and epsilon a x y, which is this one, okay, and that and this, epsilon x and epsilon y and epsilon s. And this one has the relation. Actually, this is the and this is epsilon 1. Epsilon 1 is, in terms of a coordinate, this is epsilon 1, 1. And epsilon 2 means coordinate system wise epsilon 2. And 6 is the epsilon 1, 2. Right? And this one is epsilon xx, and this is the same as the yy, and this is the epsilon, but twice of this. And this one is also twice of this. The reason we use double index is that we can easily follow the rules, cosine rules in the axis to drive these transformations. Again, what we are trying to do is that we have a strain here, we have a strain here, and what will be the relations? And this is the very easy way to drive a relation between these two strain components is that this x, this is x, force index, this is the 1. What is the angle? I will redraw the coordinate system here. This is the x1 and x2, and this is the x and y, and this is the theta. Now, again, the force index is x and 1, x and 1, x and 1 is the what? Theta. Cosine of theta is the, of course, cosine theta. And second one is also x and 1, and x and 1 is the cosine theta. So cosine theta and cosine theta, for the cosine theta, we just use the m. That's why we have a cosine theta, so m squared. Well, this table is the same as that one. So epsilon xx has the relation with the x prime as a cosine theta. Now, how about the epsilon prime and epsilon prime? Epsilon y prime and y prime, same procedure. We have a x and we have a now x y prime. And here we use the x here, and y prime is what? This is the y prime or x2. So this will be the cosine theta of this. This will be 90 minus theta. So we have a sine theta. And also second index x and y prime, same one. So we have a sine theta, so n square. And we do the same procedures, x and x prime and x and y prime. There will be a cosine theta and sine theta. And there is another term in fact, because y prime and x prime, and we have a cosine theta and sine theta. So rearrange this term is simply now epsilon x prime is the epsilon x, and x prime now m square and n square, and here we have a twice of epsilon x prime and y prime and n times n, but this twice of x prime y prime is now we call a epsilon s. So that's why we have a m square, n square, and n times n. And Well, we just change the coordinate system. As I said, prime will be the same as 1 to 6. So epsilon 1 and epsilon 2 and epsilon 6. We do a same for epsilon yy, and we have a yy, and xx, we have a sin theta, and we do the exactly same procedures, but different axes. You will see this is the n square and m square, and there is a minus mn. M square, and minus mn. And now epsilon s, again, exactly same procedures. What is the angle and between this and that and this and that? You will have minus twice mn and minus twice mn and m and minus m means again the cosine square and sine square. Okay, so this is the relations. And this is a strain transformation. And when you study about the Mohr circle, where you learn about the strain transformation, this is the exactly same result as the studied in Mohr circle. And same for the stress transformations, m and n, and this is the ob axis and on axis. We have a transformations, and t we just call t sigma, and we will call this one as the t like this transformation. So this will be a 3 by 1, 3 by, this is the 3 by 3 matrix, and strain transformations. And here is the stress. And now always we need to remember that the stress can be transformed from either this way or that way. So that's why we have a whether plus and minus. We need to be careful, but the result was very simple. We just took the minus theta instead of theta. And here is the same thing. Here we use the cross directional transformation of the strain. So this one and that, we have a strain in this direction, and then we like to obtain the strain and positive rotations. That's why we have a positive rotation strain. So this is the strain positive directions. And this is the transformation for the sigma plus a positive direction. And this is the also a transformation matrix. Very similar to a strain transformation, but the only difference will be there is the a term and twice, and there is a no twice. And compared to this, well, you don't. I recommend you to fully drive, but you don't have to memorize them. You can always refer to this table. Back to these stress transformations. Okay, back to this transformation, and as you can see, the concept is that in vector we have this is the m and n. This is the minus m and n. So this is the table we can multiply. For the strain, we have a 3 by 3, and stress, we have another 3 by 3. And the understanding this transformation would be very useful to understand this figure. See, here is the strain, and when you go to a strain from here to there, you multiply strain transformation, and here also you have a stress. Here, this is the on axis, and here is the off axis stress. If you like to drive this off axis stress from this on axis, what do you want to do? Well, this is the coordinate go backward, right? Coordinates go to from this is this. You want to go to here, go back. That's why this has to be a T sigma minus. Okay, so this is the minus. So from on axis to off axis, you need to multiply that. Again, just from positive to negative directional rotation, all you need to do is just put the minus theta. Okay, so again, the purpose of this chapter section is to drive the off-axis stiffness. Okay, off-axis stiffness. And again, the definition of off-axis stiffness is the stiffness between the off-axis stress and off-axis strain. How can we drive this off-axis stiffness? Well, we will use on-axis stiffness, which is given, and then using the theta. So Q bar will be given in terms of a Q and function of a theta. Graphically, this is the very important representations. Please understand this flow. The definition of the Q on axis is that C sigma equals Q epsilon. So this one is the on axis sigma, and on axis epsilon, and the Q matrix is the relation between on axis stiffness and strain. And now what we like to drive, is the strain in off axis and stress is off axis. So from strain to stress, what you want to do, we need to multiply the Q bar. We need to multiply this is strain, okay, this is the component, this is the epsilon bar, and this is the sigma bar, and given epsilon bar to drive this sigma bar, we need to multiply Q bar. So we multiply Q bar, and we are given Q here. So again, please don't forget to drive the Q bar in terms of a Q and theta. As we just covered, there is a transformation matrix between this epsilon and epsilon bar. What is that? Well, that is the epsilon bar and epsilon. There's a transformation matrix. And also, here is the sigma on axis and sigma bar off axis. And from here to there, we need to have the stress transformation in the negative direction, because this will go this way, right, and go this way, and this one will go to here and go that way, plus, and we go this way. So we need to have this and that. Now, again, what we like to do is to drive this one this way. Right, this way, we multiply this and Q bar, and we will have a sigma bar. But to drive this Q bar, we will use, first we need to go this way and that way and go that way. that will be the same as the Q bar. So Q bar, to derive the Q bar in terms of a Q, we first need to transform the strain and multiply by Q bar and stress transformation this way. So that will be equivalent to just the Q bar. So Q bar, I will rewrite these equations, and starting from this, epsilon equals T bar, and this epsilon has the relation this sigma, we have a relation of this. And finally, we will have a relation this and that. And that is the Q bar. So starting from here, Q bar equal sigma minus fraction. What is a sigma? Sigma will be Q epsilon. But what is the epsilon? Epsilon will be T strain plus and epsilon bar. Right? This graphical representation can be replaced by three terms: these multiplications, transformation, and this Q, and these strain transformations. Now we have this equation. What can this term be? This term is now, by definition, is the same as the Q bar, right? This is sigma bar and epsilon bar, and Q bar is now given as like that. So as we expected, the Q is the own axis stiffness as and function of theta. We will have a Q bar, and this is the nothing but Q bar. The Q is the material property, and T sigma and T epsilon is the function of its stress. And here, so using these terms, that's exactly what we just tried. Sigma bar is given as the sigma, and now sigma is given as the own axis stiffness, and this own axis strain is given is in terms of epsilon bar. So multiply this, that, and we will have this, and that is the represented by the Abd stiffness. So Abd stiffness will be given like that. We just a 3x3 matrix, and also a 3x3 matrix, and also a 3x3 matrix. We consecutively multiply, and what as a result we will have these relations. So again, this Q bar, we will have a 3x3, and actually 9 terms, but is always a symmetric, and we have a 6 terms. And Q, basically we have a 0 terms, and here is the own axis. We have only 4 terms, 1, 2, 3, 4. So this is the own axis, and this is the Abd axis. So this is exactly what we expect. Again, this is the stiffness matrix, own axis coordinate system. This is the Abd axis, stiffness, and these are a matrix. It's all function of theta. M is the cosine theta, and N is the sine theta. And you can see all terms is 4 times of this is a fourth order, twice, which means also fourth order, and all terms are fourth order sine or cosine and theta. And this is the table we need to. We don't have to remember, but we can always use this table. Okay. So once we have this, we can directly calculate from the on-axis. This is the understanding of the fourth order tensor transformation. Actually, this one we use only two index Q11. For example, Q11 is not the fourth order, I mean the second order. So actually Q11 is the one means actually this comes from a sigma 1, right? And this one comes from the epsilon 1. And actually this one is the sigma xx, and this is the epsilon xx. So this one actually Q xx xx. And this is a fourth order tensor. And if let's say you really cannot find this table, what can you do? Well, you can derive that exactly the same way as we did for vector transformation and strain and stress transformation. In other words, and this is the x prime, something like that. And this is the sigma xx, qxx. This is the qxx, basically. So the angle first index x prime x. Again, I will draw the coordinate system. This is the x prime and x y prime, and this is the x and y. Say this is the x and x. I mean theta. So this x prime, this is x, and the angle between this one will be all cosine theta. So 4 times cosine theta, 4 times, and this is the y. So this is the q prime and y. So that will be a sine. So 4 times, I mean the 4 times of a sine. And this is the x prime, xx and y. So 2 times, so multiplication of a cosine and sine. And we do consider as many terms as we have. And this and that, xx, y, and xy, and or yx, and xy, in all terms. And this is the all sine term. That is the equivalent to these terms. But I'm sure you can always find this table from our lecture note or from any internet. But it is also useful to understand this way. Just one reminder that Q, as we know, the Q matrix you can see actually this is the Q on axis. We have this is actually a 0, right? And the same as in the compliance matrix. The reason is that the x and this is here. We have this on axis. When we multiply this one, this will not change, will not cause any shear deformation. So sigma 1 and epsilon, there is no coupling term. So there is always a 0 because of a symmetry. That is the characteristics of this coupling term on axis. But in off axis, I like to emphasize there is a non-zero shear strain. This is non-zero. This is very obvious. Let's say if we the sigma 1 in off axis is on axis, and when we apply this sigma 1, we will have a epsilon 1 and epsilon 2, of course, but not only this a normal strain, but also this off-axis strain. That's why the epsilon 1/6 is a non-zero. That's why we have a epsilon 1, Q16 is the, given in terms of all these terms. This is important to notice. And now we can drive the off-axis stiffness. Well, actually, we just understand this table. That's enough in calculations. But useful to understand further, there is the relation. This is the cosine theta. Force power of the cosine theta is equivalent to cosine 2 theta and 4 theta, and this is the relations cosine. And if we use this one, then instead of that, we just put these relations and into that table. Then we can get the Q11 this term. And now in terms of U11, U1, U2, and U4 and U5. Well, what is the U1 and U3 and U5? U1, 2, 3, 4, 5 are given in terms of this on axis. So actually, this is nothing but these relations, exactly same relations. But this one is the a little bit convenient computationally. The reason is that first we define U1, 2, 3, 4, 5 using these terms, and once we have this, we put it here, and then here we calculate using the sine and cosine, and that is the exactly same result as that one, but computationally this give us a better result because the cosine 4 times multiplication will cause some numerically there is some will cause not accurate result in the table. So it's not so much important, but very useful. Another one is that U1, 2, 3, 4, 5 can be called invariant. Invariant means that regardless of this coordinate system, U1, 2, 3, 4, 5, even in terms of this 4 term, do not change. Do not change. So this U1, 2, 3, 4, 5 are called invariant. Okay, so let's program what we have studied so far. Okay, let's try to program. Again, the final form we like to have is this compliance the stiffness matrix. And we're gonna use this table. Let's say this is the O-axis. The one we're gonna simply program, type in the Excel so that we can drive the compliance matrix and the stiffness matrix for the O-axis system. And as this will be identical, same as this matrix. Okay, this just use different form of the sine and cosine relations. Okay, let's have a 10 minutes break, and this is a 2:16, and let's get back to 2:26. Okay.
Okay. So we are programming how to calculate O-axis stiffness using the own axis, and own axis is defined from here. QXY will be these terms, and QXS is from here. And as we noticed, others are all 0. And theta is the angle which will be given, and we can say 0 degree. Later we can change. We will change. I will give it a color blue to indicate that this is the input. And the so this is the, by the way, and in terms of a degree. And now we need to, we will use the radian. Now let's define this much and give them a name. Create from a selection, create a name from left column. Now U1, we can calculate the U1 from this table, and this equal, see this Q11 times what? 3 divided by 8. 3 divided by 8. And again, this is from this table, right? And plus this, and this will be YY, and plus Q XY, and 4, and Q XX, and 1 and 2, right? This is the first row defining U1. And now other terms will be similar, and U2 will be half, like that, and this will be a minus, and that will be 2 and 1, and there's no term here. And U3, very similar, except there is the minus. And U4, similar, but a little bit, there's a minus and some number. Here is the 3, right? And there is the minus, oops, minus, right? Oops, there is a, this has to be 1 and 1, right? Take a look. Oops. This one is a 1, 1/8, and 3, and there is a minus, and that is the 4. And also U3. U3 is also, this is the 1. This will be 1. Okay. And U5, this will be similar to U3. I will just copy this one. And then there will be a plus. Okay, so this will be a definition of a U. Again, this U1, 2, 3, 4, 5 is the, they are called invariant. Invariant means that they don't change over the coordinate system. Now Q, 1, 2, 3, 4, and these 6 terms will, we will follow these tables, and the I would like to, okay, so this Q11, see here, U1 times U1 plus, and U2 times what? Cosine a theta, but again, theta is the degree. We need to change to a radian, and the I'm sure there will be a radian. Radians. Right? And then there is the U, what is this? U3, and cosine, there is the 4 times, and there is a 2 times, right? 2 times. Okay. And Q22, we follow this table again, and there will be minus, and Q12, U4, and there is no 2 terms, right? And then a cosine minus cosine 4 theta. This will be a U4 and 3 and minus and cosine, right? Same as that one. I mean, it's Q66 instead of U5. U4, you have a U5 and U3 and minus. Okay. And Q16. Delete U2 times 1/2 and 2 and the sine and twice and U3 and this is the also sine and radian and the 4 theta. Okay. Okay. Now this just copy and instead of a plus, we just change the minus. Okay, so basically this is what we have learned today, and we just program. Program means that this will be the given and theta, and this will be the output using the definition of U environment. And as you can see, if I enter the theta equals 0, pay attention, please compare this term and that. They should be the exactly same, right? If they are not, something is not right, something is wrong. So when we program, we always need to debug and check like that. Okay, so again, make sure this term and these terms are same. Of course, when theta equals 0, because the theta equals 0, they are the on axis will be the same as what off axis. So this will be again just nothing but the on axis, which was taken from here, right? Again, this one, this guy was taken from this term, and this guy is taken from these terms, and so on. Just to redefine this on-axis coordinate system, and this Q1, 2, 3, this is the off axis, which we like to obtain. While we prefer to express this term in terms of a matrix form, so we're gonna have this matrix form, and this will be Q11, well, this term will be Q12, and this will be Q22, and this will be a Q16, and this will be a Q26, and this will be a Q66. And this will be the symmetric. Okay, so this is the AQ matrix, and okay, I will move to here and compare this guy and that guy exactly same when angle is 0. It's obvious. Now, similar to this, I just like to copy this form, and the now O axis is the epsilon O axis, and sigma O axis, the epsilon 1 and 2 and 6 indicate O axis strain, and sigma 1 and 2 and 6, this is the simply, indicate to O axis. And here is the strain, and this can be, well, any strain. Basically, this is the given. This will be a given. And now, importantly, this a sigma O axis will be a Q matrix times strain. And here we need to define this. This has the epsilon O axis. We will define as the this is the defined as the O axis, and this will be defined as what? Defined as the Q O axis. I want to double check what did I, Q matrix. Okay, Q matrix. Now I like to define Q of well, Q matrix and of. So to calculate this term, we need to have this one now U O axis, and this one we need to have a of, right? Just for confirmation, let's have a same as that one. And obviously this is the has the same, because this O axis stiffness, O axis stiffness, this is the a Q bar, will be exactly same, just because the theta equals 0, right? Now, if we change the theta as the 45 degree, now you see the many terms. The Q O axis will have a values in O axis. Well, it's not easy to predict. We need to go through this, transformations. Okay, so I think that this is the well programmed, but always after program we need to double check. We need to double check. I would like to have this one. Cannot change part of any array. What is array? Oops, I made a mistake. Okay. After program, we need to always double check these are all well programmed. So we check the 0 and make sure these values are same as these terms. They are. And 45, well, 45 is easy to confirm, but the one for sure is that this term and that is the same. Why Q11 and Q22 are same? Well, since the 45-degree transformations, say we have we have 45 transformations. That's 45. Then the stiffness in this direction and stiffness in this direction will be the same. That's why we have exactly same, right? Because of this is the 45. And the shear stiffness, well, not easy to predict, but we do have some value. Very importantly, we have, say, we have a 45. When we have the tension, this will deform. This will deform with a certain angles like that, right? So epsilon 6 is not 0. This is the a sigma 1. That's why we have this is the Q16 is a non-zero. And that is the same as the Q16, Q26. Again, they are symmetric, and it needs to be same, and this has to be same. This is the one thing we can and we can check. So through these checking and values, we are understanding more and more about the composite behavior. So please just try to understand the how these values are changing according to a value. Now let's try to transform the 90 degree. What if the angle is 90? Well, 90 degree, the value the coordinate system is now rotate by the 90 degree. What it means? It means that the QXX will be Q22 and Q, see here, QYY will be Q11. So 90 degree rotations, this one and that one. So this one will be Q sigma 1 and sigma 2. So this 90 degree material property, which is this one, will be the same as the on axis, right? So and this one is the these terms, and that well does not change. And now this 0, this is a 0, but looks like a non-zero, but this is a 0 because pay attention to order. Well, we cannot avoid this kind of a numerical the small values, because this calculation is involved in the sine and cosine. But anyhow, this is a 0. So here, this is the way we checked. And again, once the main purpose of driving this off-axis stiffness matrix is that once we have an off-axis strain, and we are able to get the off-axis sigma. Okay, that's the main point. Now, instead of enter some few angles, we can get the automatic values using the macro. Let's do one more step. One more step means that let's try to have off-axis a compliance, and off-axis compliance is that. Let me double check whether we have that sections. Okay, so compliance is this. Now matrix inverse of this guy. So this is the off-axis compliance. That this is the 3×3, and inverse of the stiffness. And now we can define the material property in the off-axis, E1 and E2, and Poisson's ratio, and ES, I will call E6. And there are another Poisson's ratio, but let's just define this. And this term, I'll write down. This one, this is the sigma bar and Q bar and epsilon bar. Now, here epsilon bar equal S bar and sigma bar, and this is the S bar. S bar is the inverse of the Q bar, which we have here. And once we have a S bar, by definition of a compliance, we can say E1 and Poisson's ratio. This is the equivalent material property. Very important form is that this epsilon 1 and the E1 and E2 and this one. Okay, there is the we can define the Poisson's ratio for coupling term, but let's do it later. Importantly, E1. This is the simply what? E1 will be inverse of the S11, and E2 here is the inverse of S22, and this mu1, say S6, 1, 2 is the mu1 E1. So how do we get this mu1? Mu1 equal S12 divided by S11, and E6 is divided by the S66, which is not in our class note, but is can be very useful information. So this at E1 will be a inverse of this S11, and this one is the also inverse of these terms, and this mu1 will be a this divided by this. By the way, we need to have a minus here. And this one will be 1 divided by the S. The reason we have a minus here is because we have a definition. Because of this definition, okay? Okay, so I will give them a name. The reason, again, I'd like to remind you again, this definition of engineering constant. Let's say we have this x-axis, we apply the sigma 1, and experimentally, what can you measure? You can measure the sigma 1 versus the epsilon 1, and that is the a slope. Let's say you put some strain gauges, and this is the what? This is the E1, as we define here. Okay, this is the E1. Exactly same as define the material property, engineering constant as in other materials, on axis and isotropic exactly same, but it's useful to be able to drive these terms from all the way through a on axis. And please remember that all the stiffness matrix is defined from this on axis. It's EX and EY and the S and Poisson's ratio. This is the material property in on axis, where this is the micromechanically calculate, but this also can be also measured from experiment. Now all the way through on-axis stiffness, off-axis stiffness, off-axis compliance, and this will be the output, right? This is the output, and the okay. So first, let's see how this value is changing along with this angle. If we change this angle, say angle 0, pay attention to these terms. This will change. And that will be the exactly same as what? Same as the stiffness, the on-axis engineering constant, right? Exactly same. And if we enter the 90 degree, and these terms will have exchange, and so on. Now let's try to E1 and E2 and Poisson's ratio and E6 and Q1 to okay, so this one is the defined taken from here. This will be the output, by the way, this quick chart. And E1 is the taken from this value. And this Poisson's ratio is from and here. And shear modulus will be here. Let's forget the other terms, okay? Only this 1, 2, 3, 4 terms, and this one now input will be a angle. Angle means that this angle will be the given, and this will be the output, right? So here the angle will be taken from this value, and so on. So what we are trying to do is that, I hope you are able to see this flow. This value, okay, this is the final a form. This one will go to what? This angle. No, this is not the no longer. So this is the angle, and that is the angle, let's say, for example, 0, and goes to here. And then this will calculate that one, and all the way here. Now I will do it one more time. This one goes to here, and go to here, and go to here, and go to here, and go define the stiffness, and finally back to here. So basically this will be the input, and all the way through the theory we just learned, and the output will be these terms. Okay, so I will change this the output as the in red, and this is the input as the in blue. Okay, so I will change the name as the OVX. OVX is called stiffness. This is the name of the new worksheet. Okay, so we learn initial value is the angle now from 0 to 100 degree, 180, and the angle is the by degree of 1. And let's do that. And this is the one we got. And as you can see, OVX is stiffness. And again, this we enter here, OVX is stiffness. That's why new worksheet has been created, OVX is stiffness. And all the output is the calculate along with angles from 180 degree automatically. And also pay attention to definition of this. And this is the 0 degree, 121, exactly same as the input we have. See here, on axis, stiffness compliant, the stiffness engineering constant is exactly same as the on axis, simply because this is a 0 degree. So that is the chart, and let's see. Okay, I will divide by them into a different chart. Only say, oops. E1. And this and that, like to show you only E2. Like to show you only Poisson's ratio. Well, okay, Poisson's ratio, and only shear engineering constant. So as we expected, well, not easy to expect at this point, but the angle is changing from 0 to 180 degree, and the stiffness, Young's modulus, E1, and go to from here to 90 degree and 180. And as you can see, 180 is going back to original coordinate system, and so on. original coordinate means that, say we have a angles like that, and this, and that is the theta. And theta, if theta is the 90, and theta is the 100 degree, is back to original position. So if theta is the 0, this is the E1, I mean same as the E-axis, and this 90 degree will be a EY, and this is the for E2, this will be a EY, and here it will be the EX, and Poisson's the Poisson's ratio, and that will be the mu x, and very interestingly, 90 degree, this will be a mu y, and goes up and down. And shear modulus wise, this is the ES, and reach the maximum at 45, and back to ES. Okay, so this is the very interesting, I mean, obvious observation, but very important observation. Let's try to plot only 0 to 90 degree. As you can, the reason is that, as you can see, this part will be just a repeat, and this part is nothing but a repeat, right? This is the only repeat, has to be same, simply because a 0 to 90 and 90 to 100 degree will be the exactly same. So you can go back, and here, say OVX is stiffness, I'll say a different number, 1, and then replot from 1 to 90 degree, and every angle 1. And now we have a different worksheet. Now in this case, angle from 0 to 90 degree. And here only E1. And here is the E2. And here is the Poisson's ratio. Here is the shear stiffness. Okay, exactly same, but I just like to emphasize that they are repeating after after 90 degree, exactly same. I like to double check. And again, the value wise, I will make a new window and view and arrange your tiled and horizon vertical. Okay, so I will open two same worksheet but two different window, and here is the as you can see, EX, EY, and so on. And here, as you can see, I just want to double check again. This is the exactly same as the on axis, and also here 90 degree. The material property of the E2 will be a EX, and E1 will be a EY, because the angle has changed from X to exchange, right? And the shear will be the same, and the Poisson's ratio will be the as you can see now, the Poisson's ratio of the Y. See, this is the same one. So this is the another conformations and very important observations. Okay. So any program, FM program or CA tools or any analysis tools you been using or you will use will follow this kind of relations, and you need to have a tools. You need to understand the theory. You need to have a tools like this. So always a double check. So the tool you are learning right now will be your tools, and even after class, after this course, it will be very useful for you to be able to use this kind of tool to double check this stress transformation and material transformation and so on. Now I like to save as three, okay. Please follow the version name so that you can understand better. You can follow our class. Okay, so now we complete a class of how to calculate the off-axis stiffness. And of course, there are several equations and several derivations. But most importantly, what you need to understand is that the purpose of this section, is to calculate sorry, where is it? Calculate this off-axis stiffness, okay? Given on-axis, and now we like to calculate the off-axis stiffness. You need to understand definition of a strain and stress in off-axis. You will understand why this derivation is so critical in derivation of composite analysis. Next chapter will be a stiffness of a composite laminate. Stiffness of a composite. Now, laminate, okay, laminate. Laminate means now we have a multiple plies with a different angles, which makes one composite laminate. So that plate or laminate will have a stiffness. So laminate sequence and off-axis and so on. And this is a core theory of we call a laminate theory, classical laminate theory. Again, we have a composite laminate like that. Okay, composite laminate like this. Each one will have a different ply with a different angle, ply angle. In the previous chapter, we understand how to calculate off-axis stiffness of each ply. Now, many plies are stacked up and make one laminate like this. And to indicate laminate sequence, we use 0, plus minus 45, 90, and sometimes the S here. S means symmetric. So symmetric means starting from always a bottom, 0, plus 45, 0, plus 45, and minus 45, minus 45, and 90 degree, and symmetric. symmetric means that we're starting again as 90 degree, minus 45, and plus 45, and 0 degree. So this means that A plies and stacked. Here, very important, this is not just a stack. They are all glued. Glued. We need to keep that in mind. All plies are glued together. They don't behave independently. They behave as a glued laminate. Glued laminate. Each ply has with its own ply angle. Now, since they are all glued, and consider this laminate as one plate, and there is a strain and curvature as a given, as a normal strain. Say we have a laminate and we apply a whatever strain, any load actually, any load, and always has a strain distributions through thickness, linear dependency. See, through the thickness, this is the z-axis, this is the x1 and x2, this is the ob axis. And now any load, we don't know what kind of a load we apply, but the strain is always the strain distributions in terms of a z, okay, in terms of a z. In terms of z means in each ply has the coordinate z, has the constant term and linear term. Linear means as a function of a z. So any strain has the term of the, as you can see, always a linear strain like that for any load, okay, any load. This one we can divide by this uniform. Uniform is this much, and this is the linear term, and linear term is the as this linear distribution. That's why we multiply z, and this is a curvature. Okay, k is the curvature, and z is the coordinate system. Now we need to understand where is the z equals 0 locations. Well, z equals 0 is always the located in half thickness. Very easy. At the middle, half thickness means that middle plane. Which is different from a neutral axis in beam theory. Okay, neutral axis, beam theory in neutral axis always located where strain is 0, but here z equals 0 is not a neutral axis, but just a middle plane. Easy to select. So normal and shear, same. Always a uniform, and there is a linear dependency. Okay, so in matrix form, this is the ob-axis strain, this is the uniform strain, and this is the linear term. And each one we have a curvature. The reason we have a curvature is that to have a linearly varying strain, we need to have this kind of a curvature. See, this is a band, then top is always the positive strain, and bottom we always have a negative strain. Positive and negative strain. To have this, we need to have all kinds, always the bending like deformation. So K1 actually is nothing but 1 over R, R is the a radius of this curvature. So in short, we can say this is the in-plane strain. Okay, this is the in-plane strain. Oh, I'm sorry, this is the in-plane strain, which is a uniform, and this is the curvature, and this is the relate to a bending. Okay, let me ask you again, why do we have this kind of a strain distribution? When do we have this kind of striation? The answer is that all plies a stacked and glued. Okay, when plies stacked or laminate and glued, so laminate means that always glued. They don't deform independently. If they not glued, what will happen? When we have a strain, the strain may have, when we have a multiple stack, if they are not glued, the deformation will be, sometimes like that, discontinuous, right? Discontinuous strain. It doesn't happen. Cannot happen. Why? Because all plies are glued and stacked. In that case, the deformation has always the uniform and always have a linear form. Only two physical quantity, uniform and linear bearing terms. And there is a Z. And Z equals 0 is always located in the middle plane. Okay. Now, well, that is the redefined. I mean, to introduce the help you to better understand of this bending and twisting. These terms, Q1 and Q6. And now, okay, this is the strain distribution. Now we like to define the load we apply. The load we apply to this laminate. We call in-plane load and bending moment. We don't apply load each ply. We apply the load to laminate. So there will be a load. We have a laminate. We have a multiple laminate. We now have a load. This is a load now, not the stress. N1 and N2 and N6. So this is the in-plane load, 3 in-plane load, and 3 bending moments. 3 bending moment will be, and here we apply a bending moment. This is the moment 1, and this is the moment 2, bending, right? This is the bending, and this is the bending, and also a curvature. I just want to double check this sign. Let me just use this okay, M6. This is the twisting moment we are applying. Twisting moment, and twisting moment, and the less up. Okay, this is the twisting moment. Well, it looks a little bit complicated, but this is nothing but the combination of in-plane load and bending moment. And this is the, again, the N1 and N2 and N6 we are applying. And this is the bending moment, M1 and M2 and M6. So 3 in-plane and 3 bending moment. From the definition of this in-plane load, please remember this is not the stress, this is the load parallel to plate and load. That's why the in-plane load. And N is the force. Actually, N1 is the force we are applying is like that, but divide by this much length. Okay, this is L, divide by L, that is the N1. So we are applying certain load, but divide by the L is the N1. So N1 is the force per unit length. Please remember this. And if we divide by this H, N1 divided by the H will be a sort of equivalent stress, right? Equivalent sort of a stress. But we don't apply the stress, we apply the stress in-plane load. So by definitions, N1, now this figure is better. This one, actually, we are applying the N1, but we don't know how this sigma is distributed. We don't know. But we do know later, we do know the strain will uniform, I mean, the linear variation as we studied before. But we don't know the precise stress distribution. All we know is that the stress is different from ply by ply because we have a different material property. But we do know that summation of a sigma 1 integration over the z-axis only will be the N1. And same for N2 and N6. That is the definition and relation between the in-plane load and in-plane. This is the what? Off-axis stiffness, and this is the in-plane load. For the moment, bending moment, we don't know, as we notice here, we don't know the precise stress distribution, but by definition of a moment, we will have a sigma 1, Z is a force, and Z, we multiply Z to have a moment. So M2 is the same. Here we have a sigma 2 bar, and we have a multiply Z, we have a M2. And M6 is a shear, is a little bit difficult to visualize, but conceptually exactly same as a Z. So if we use the vector form, this is the sigma bar, and this is a sigma bar, but here is the Z multiply. And moment is this 3 term, and this is the 3 term. Okay. And now let's combining all these in-plane load and bending moment. The purpose of this chapter is to relate a stiffness of this matrix. Okay, the purpose of this chapter, again, the chapter is to calculate the stiffness of a laminate. What does it mean, stiffness? Well, stiffness is that always the deformations and load, right? The deformation in this laminate and load in laminate. And what is the deformation? That is the one we will study, and load is the one we are studying right now. And we are now combining all the equations we have learned so far. And strain, as we studied, the strain has the uniform strain and curvature, and there's a Z. And previous section, we already studied the off-axis and off-axis strain. This is the Q bar. This is the off-axis stiffness, right? And we just programmed that this is off-axis stiffness can be derived from on-axis stiffness and angles of each ply. This is the each ply, right? And this is the laminate. From this is the laminate, and laminate is strain. And now here, this guy, what is this? This is the off-axis strain. And off-axis strain, I would like to remind you again, a certain ply, this is the certain ply. This one has the sigma bar and Q bar and epsilon bar. Now, this one has a coordinate system as a z-axis. I mean the height as a z. So this epsilon bar is the off-axis strain, but now from this laminate, we notice that epsilon zero in-plane strain and curvature. So this is the Z, which is the location of this ply, and that is the strain given in terms of a in-plane strain and curvature. So this epsilon bar will go into here, and now we have these equations, epsilon zero and curvature. Now we have a definition of in-plane strain, and that is nothing but the sigma bar integrations and moment sigma bar multiply Z integration. This sigma bar, we have this one and we put it here. And this sigma bar, we put it here. And then from now on, this is nothing but numerical, I mean the analytical mathematical derivations. See here, there is epsilon zero and curvature, and epsilon zero has nothing to do with the Z, okay? Z and K is nothing to do with the Z. So all is left in the integration of integrand is that Q bar integration of Z, and here we have a Z times Q bar and Z, and here, and K, again, K is independent of Z, so can be out of integration. So this is the N, and moment is from here and multiply Z here. So now we have a Z term, and now we have a Z and Z, we have a double Z here. So this term is the Z dependency. Q bar, by the way, Q bar, you remember all the derivation we have, sigma and Q, and this is the T epsilon, and this is the function of theta and function of theta, and this is the all function of Z, right? And Q is also function of Z. So certainly Q bar is the function of Z, and we need to integrate. And but important point is that epsilon 0 in plane strain and curvature is a constant over for z-axis. So this n and m is a matrix form, and ABD, right? This is A, B, B. This is happen to be the same. Well, not happen to be. There's physically always symmetric. And D is D, and epsilon 0 and K. And this is a core equations in classical laminate theory. Laminate theory, now we call ABD matrix. This is the ABD matrix. Remember, this N is the 3 by 1, and M is the 3 by 1, and epsilon 0 is the 3 by 1, and this is the 3 by 1. And ABD matrix is all 3 by 3 and 3 by 3. Why? Because the A is the defined is this term, and Q is the 3 by 3. So this ABD matrix makes a 6 by 6 matrix. So this is a stiffness matrix. Okay, now the main point is that how to program this, and we calculate all the ABD matrix for given the laminate. That is the core part, as I mentioned, and important point. And A okay, this is the one we just obtained from strain distribution and definition of a moment, the load. Now, how to calculate numerically? Well, by definition of A is the Q bar, integrations of Q bar, and from bottom to top. And now to calculate this one, see this one, we have many we have a plies, right? We have many plies, and say this is a z equals 0, and from here to there is the total thickness is h, and here is the z equal h over 2, and here is the z equal minus h over 2, and a certain ply. This one has the sigma bar and q bar and epsilon bar. And so in this ply, of course, the q bar is the constant, right? Each ply, q bar is the constant, but q bar is the what function of a z, because ply by ply, we have theta 1, theta 2, and theta 3, and so on. So each ply, we have a different q bar. But here is the Z1, Z2, each Z, we have a q bar, and summation of each ply. So ply, let's say this is a k equal 1, k equal 2, and up to k, this is the k equal n. So this is all the ply number. N is the ply number. And each ply, we have a zk to a gk plus 1. And obviously, within ply, this Q is the constant because of each ply. So integrate Q is the constant, and then if we integrate this ZK1, ZK, right? So this A matrix is simply a summation of this Q bar times each coordinate. Well, this is nothing but the each ply thickness. And also a B matrix, you know, the B matrix, B is the same as that. B matrix, by definition, we have a Z here from bottom to top, and we have a number of plies, very same as previous. And now we remember we have a Z here, and each ply, this is each ply. Each ply Q is the constant, but Z is not. Of course, Z is a integration Z. So if we integrate, this is the integration, and remember this is the KKK, and K equal 1 to N. This is the definition of a B. Now bending this D, okay, D is the definition, Z square, and this is the within ply, this is the over the ply, and integrate. This is the constant within the ply, so out of the integration, so this is the integration, and if we integrate, this is the integrate by, this is a ZK, and this is a ZK plus 1, and this is the integrations, okay? So here is the how we calculate ABD matrix numerically, and so this is the where we need to program again to calculate a ABD matrix. Again, once we have an ABD matrix, this is the stiffness. This is the stiffness. This is the this is the stiffness matrix of the laminate. Okay, laminate. So a strain or curvature and load and moment. This is the stiffness. Stiffness matrix will be calculated from each x-axis, which we just learned, and coordinate everything. Take a look at. All we need to have is have x stiffness of each ply, right? x. Okay, well, I want you to program this to calculate the ABD, but is sorry, we are out of we don't have enough time. But I'd like to close today's class. But this ABD is the core part, and the just to make sure the class, I mean the homework I'm going to assign today is to calculate a ABD matrix of each terms. Okay, you need to calculate ABD matrix of a laminate. This is the how to calculate the ABD. Again, the most important is the you need to calculate the Q bar, right? Q bar here. This is the Q bar. But for each ply, you need to have a location Z and Z. So homework number 5 is to calculate the A, B, B, D matrices for the given layout. Let's say 0 plus 45 and minus 45 and 90 degree and symmetric. All you need to do is very important to calculate this guy, and each ply, let's say, have a ply thickness is Q. Let's say you have a Z1 and Z2 and Z3 and Z4 and so on. So each one we have a thickness. I will arrange like that. Okay. And now say this is the A plies. The ply thickness will be say 0.125 millimeters. Well, some numbers, and this will be the ply thickness. If 8 plies, then total thickness will be what? 8 times this ply thickness, and this is the total thickness. And now Z1, what is the Z1? Z1 will be a total thickness divided by the half and the minus. That is the coordinate system, right? And then this one will be this plus a ply thickness and so on. So as you can see, the 8 plies total thicknesses will be 1, and bottom to top, and this one you can say Z5 and Z6. You better use different symbols, because, well, it doesn't matter that much. So each one we have a coordinate, and this is the this ZK1 plus 1 k, and this is the how you get the z 1, 2, 3, 4, 5, and 9 for the case of the 8 plies, right? So you can say this is the z, I would say k. Okay, this is the zk, like a vector. And as you can see, A11, you will have a A11 and A12 and A22 and A16 and A26 and A66, 6 terms. And you will have a from these definitions, okay, from these definitions, you will see this one will be Q. You already have a Q11, right? You already have a Q11, and times, just follow this equation, times what? The k plus 1 means this guy minus, okay, minus that guy, right? And next one, and next one, you just this is the A11, but you need to remember that this is the you need to recalculate Q matrix for each angle, right? So each one, let's say this is the theta, you can have this is the 0, and from this is the 0 angle, and 2 and 3, this is the 45, and this is the minus 45, and 90, and 90, and minus 45, and plus 45, and 0 degree. What is missing here is that the Q11, I'm sorry, just 1 minute, okay? So each angle you should get a Q11 and Q12 and so on. And this one, Q11 should be this guy, which you will calculate depending on this angle. And this one, a Q11 will be this guy. So you calculate up to here, and now A12 will be same as that one. Just so Q11, Q12, Q226 should be calculated from equation we have, right? So this one, Q11, So far, but this is the angle. This is the angle you need to have. And you don't have to make the automatic program, but any way you prefer, you calculate a matrix and so on. Now, finally, what do you need to do? You need to summation. You need to summate. You need to sum all these terms, which will give us the ABD matrix. So that is the finally a ABD matrix. Well, same for the B matrix and D matrix. Same for the AB B matrix and D matrix. And you can say this is the B. And this can be a D matrix. So you do very similar patterns like this. And as you can see here, B11 as the exact this term and that. But as you can see here, we have a little different terms. Say this is the square. See, there is a square, and there is the square, and there is the half. Okay, there's a half. And you do exactly the same, and copy, and the paste, and you sum them up. That will make the AB matrix. And now for the D matrix, we follow the same. And now this one has a, instead of 2, we have a 3, and this is the 3, and that is the 3. I mean 3. Okay, so others will be the same, and this also are same. So this will give us all the ABD matrix for the given Q11 and all the Qs and 4 different angle. See, remember, you need to calculate this is the Q corresponding to theta. And you have to have a different Q for this, and Q and for that, right? That's one you need to do. And this is the Z coordinate, and this is the how you calculate the ABD matrix. Okay, so this is the a homework and for the givens. And for your help, I will share this Excel file for your homework. Okay, only one problem, but you need to fully understand not just the programming, but also a theory. Okay, that's what we like to cover today. Sorry, it's a little bit over time. And if you have any questions, is there any questions you'd like to ask right now? Again, the topic we cover is the core part of the classical laminate theory. This is the main part of the laminate theory, and all the CA tools, FM, like ANSYS and Abacus, has this theory in the program. Share element, especially share element and beam element, they all have this kind of program. And you need to have your own tools. And this is the most important a part of the composite theory. And the okay, so this is the end of today's class. If any class, any questions, please share your question through a catalog, and be sure to have this a report little bit earlier than due date. You guys always, submit the homework just 1 day before, but I recommend you to do this homework now. It's much better than doing the last day. Okay, thank you so much, and well, have a good weekend. Thank you.